7QC tools individually, let's first understand this complete overview. This image summarizes the 7 quality control tools, which are considered the foundation of quality assurance and continuous improvement across industries worldwide. On the top right, you can see why we use 7QC tools. Their main purpose is to collect, analyze, and interpret data in a structured way. Instead of making decisions based on assumptions, these tools help us identify the actual root cause of problems and improve processes using facts. On the right side, you'll also notice the founder section. These tools were popularized by Dr. Kaoru Ishikawa, a Japanese quality expert who made quality problem solving simple and practical for everyone, from operators to quality engineers and top management. Below that is the global recognition section. Today, the 7QC tools are used in almost every industry, including electronics manufacturing, automotive, aerospace, healthcare, pharmaceuticals, food processing, and many more. They are also a key part of lean manufacturing, Six Sigma, total quality management, and ISO quality management systems. The center table introduces all 7 tools. Check sheet for collecting data. Fishbone diagram for finding root causes. Histogram for understanding data distribution. Pareto chart for identifying the most critical problems. Control chart for monitoring process stability. Scatter diagram for analyzing relationships between variables. Stratification for separating data into meaningful groups to uncover hidden patterns. Finally, at the bottom, the message is clear. These 7 simple tools help us understand problems, find root causes, make better decisions, reduce defects, and achieve continuous improvement. In the next sections, we'll explain each 7QC tool in detail with real manufacturing examples so you can confidently use them in your workplace. C tools. The check sheet, which is the foundation of quality data collection. A check sheet is a simple yet powerful tool used to record defects, events, or observations in a systematic and organized way. Instead of relying on assumptions, it collects real-time data directly from the production line. As shown in this example, every time a defect such as a solder bridge, missing component, tombstone, or misalignment is found, a tally mark is recorded. By the end of the inspection, we can clearly see which defect occurs most frequently. The main benefits of a check sheet are accurate data collection, time savings, easy trend identification, and fact-based decision-making. It's commonly used during production inspections, process monitoring, quality audits, and defect tracking. Creating a check sheet is simple. First, define the problem, identify the data to collect, decide the inspection period, design a clear format, collect data at the source, and then analyze the results using other QC tools like the Pareto chart or Fishbone diagram. Remember, without accurate data, no quality analysis is reliable. That's why the check sheet is always the first step toward effective quality improvement. The most powerful tools for problem prioritization. A Pareto chart is a combination of bar graphs and a cumulative percentage line. The bars are arranged from the highest to the lowest frequency, making it easy to identify the most significant problems. It is based on the Pareto principle, also known as the 80-20 rule, which states that approximately 80% of problems are caused by just 20% of the causes. Instead of trying to solve every issue at once, we focus on the few critical problems that have the biggest impact. Let's look at this SMT AOI example. Here, solder bridge, insufficient solder, and missing component are the top 3 defects. Together, they contribute to nearly 80% of all defects. This means that by focusing our improvement efforts on these 3 defects first, we can achieve the maximum quality improvement with minimum time, cost, and resources. To create a Pareto chart, first collect defect data using a check sheet, arrange the defects in descending order, calculate the cumulative percentage, and then plot both the bars and the cumulative line. A Pareto chart is widely used in quality assurance, manufacturing, Six Sigma, lean manufacturing, and root cause analysis because it helps teams prioritize actions, improve efficiency, and make data-driven decisions. Remember, don't solve every problem first. Solve the most important problems first. That's the power of the cause and effect diagram, also known as the Fishbone diagram or Ishikawa diagram. This tool was developed by Dr. Kaoru Ishikawa to help teams identify the root cause of a problem instead of just treating its symptoms. Remember, the goal is to focus on causes, not blame people. As shown in this example, the problem, or effect, is high solder joint defect. The main backbone of the diagram points toward the problem, while the branches represent the major cause categories, commonly known as the sixes: man, machine, material, method, measurement, and environment. Under each category, we brainstorm every possible cause. For example, under man, causes include insufficient training and operator fatigue. Under machine, printer misalignment and poor maintenance. Under material, poor solder paste quality. Under method, incorrect print parameters. Under measurement, SPI or gauge calibration issues. Under environment, high humidity and dust contamination. After listing all possible causes, the team investigates and verifies them using data. In this example, the root cause was identified as inadequate paste volume due to incorrect print parameters. The fishbone diagram is widely used in quality assurance, manufacturing, Six Sigma, and Lean because it promotes teamwork, organizes ideas, supports root cause analysis, and helps implement effective corrective actions. Always remember, don't just fix the defect. Find and eliminate the root cause. That's the real power of the fishbone diagram. Histogram is a graphical tool that shows the frequency distribution of continuous data. It helps us understand how data is distributed, how much variation exists in the process, and whether the process is stable. In this SMT example, the histogram displays the distribution of solder joint height. The x-axis represents the measurement range in millimeters, while the y-axis shows how many samples fall within each range. Each bar touches the next because the data is continuous. Notice that most values are concentrated between 0.70 and 0.90 millimeters, forming a bell-shaped curve. This indicates a normal distribution, which usually means the process is stable and consistent. The LSL, lower specification limit, and USL, upper specification limit, define the acceptable limits. If the data spreads outside these limits, the process may produce defective products. At the bottom, you can also see different histogram shapes, such as normal, left-skewed, right-skewed, bimodal, and out of control. Each shape provides valuable information about process behavior and possible issues. To create a histogram, first collect measurement data, divide it into equal intervals, count the frequency of each interval, draw the bars, and then analyze the distribution pattern. A histogram is widely used in quality assurance, manufacturing, SPC, Six Sigma, and process capability analysis to monitor variation, identify abnormalities, and support data-driven decisions. Remember, a histogram doesn't just show data, it tells the story of your process. By understanding that story, you can reduce variation, improve quality, and achieve a more capable manufacturing process. Of the 7 QC tools, the scatter diagram. A scatter diagram is used to determine whether there is a relationship between two variables. Each dot on the graph represents one data point. In this example, the x-axis shows solder paste volume, and the y-axis shows solder joint height. Notice that as the solder paste volume increases, the solder joint height also increases. This is called a strong positive correlation, with a correlation coefficient of 0.82. A scatter diagram helps us identify cause and effect relationships, verify process assumptions, and support root cause analysis. It can show positive, negative, weak, or no correlation between two variables. This tool is widely used in quality assurance, Six Sigma, and manufacturing to optimize processes and make data-driven decisions. Remember, a scatter diagram doesn't prove the cause, but it clearly shows whether two variables are related, making it an essential tool for quality improvement. The control chart. A control chart is used to monitor process stability over time and to distinguish between common cause variation, which is normal, and special cause variation, which requires investigation. In this example, the center line represents the process average, while the upper control limit, UCL, and lower control limit, LCL, define the expected range of variation. Most data points are within these limits, indicating a stable process. However, sample 16 exceeds the UCL, which signals a special cause and an out-of-control condition that must be investigated immediately. Control charts also help identify abnormal patterns, such as trends, cycles, or multiple points on one side of the center line, even before defects occur. This tool is widely used in SPC, quality assurance, and manufacturing to reduce variation, maintain process stability, and drive continuous improvement. Remember, a control chart doesn't just detect defects, It helps prevent them by identifying process instability before it impacts product quality. Understand the seventh of the 7 QC tools, the process flowchart. A process flowchart is a visual representation of every step in a process from start to finish. It helps us understand how a process works, identify bottlenecks, eliminate waste, and improve overall efficiency. In this SMT PCB assembly example, the process starts with PCB receiving, followed by solder paste printing, component placement, reflow soldering, and AOI inspection. If defects are detected during inspection, the product moves to rework and reinspection. If no defects are found, it continues through ICT or functional testing, visual inspection, final packing, and finally reaches the customer. To create a process flowchart, first define the process scope, list every step in sequence, use standard flowchart symbols, connect them with arrows, and then analyze the process for delays, bottlenecks, and improvement opportunities. This tool is widely used in quality assurance, manufacturing, lean, Six Sigma, and process engineering because it improves communication, standardizes operations, reduces waste, and increases productivity. Remember, you cannot improve a process unless you first understand it. A process flowchart gives you a clear picture of the entire workflow, making continuous improvement much easier.